Okay, in the previous video, we figured out these equations for the voltage in the stator, the voltage in the rotor. We remember that these are in the alpha beta reference frames. So now I'm just gonna clarify a little bit something for this. We know that epsilon, this angle that we got here, is the angle between the stator and the rotor. Also, in the previous video, we figured out this equation, R1 is the current in the stator and in the stator reference frame plus Ls plus m/2, the derivative of the current of the stator in the stator reference frame plus 2/5 3/2 LSR dt IR, current in the rotor and the rotor reference frames times an angle that will change it into the stator reference frame. Okay, so we said last time that Ls is gonna be Lis plus Lm. So this is when we put it here, this is gonna give us Lis plus 3m/2. So that's what we get here in these new formulas. And also we are going to change a little bit to simplify the formula. We're going to say that L1 is going to be Lis plus 3/2m. We're going to say that L0 is equals to 3 halves Rs, and that L2 is equals to Lir plus 3 halves Mr. Okay, so when we do these changes, we are gonna get our new voltage equation. This is gonna look like this: R1 Is plus L1 dt Is plus L0 dt and IR e to the j epsilon, and our rotor equation is gonna be R2 IR plus L2 dt IR plus not dt Is e to the minus j. Okay, so just a little bit to clarify, what does Is means? Is the stator current is the stator current in the stator reference frame. So it's the stator current when we have the stator reference frame. And similar, IR is the rotor current in the rotor reference frame. So this is important to remember because we can, for example, say that IR plus Is, we cannot add up two different reference frames. So if we want to do something like this, we will have to change this one into the stator reference frame, and that's what we do here by adding an angle. Okay, so now we can get into figuring out how the power. So we know that omega is the angular speed. We know that if we derive speed, we get angular acceleration. Also, we know that force is equals to mass times acceleration. And so we can say that the applied torque is equals to J d omega dt. And this is required for acceleration. We can also say that Tb is equals to b omega, and this is required for friction. Now J is our moment of inertia, and B is our friction coefficient. Okay. So now we are going to try the developed torque. Td is going to be equals to the sum of the two other that we just find out. So it's going to be our moment of inertia times our angular acceleration plus our friction coefficient times our angular speed plus TL. The TL is going to be our load torque. We don't have an equation for load torque because it's whatever the machine is, yeah, whatever we are running with the machine. And we can say that the power in mechanic is gonna be equals to the torque times the angular speed. Okay. Now, in a previous video, we figured out that power, when we have our reference frames A, B, and C, now our time reference frame, we could write it like this, A and B. So these are our phases. And we figured out that this was equals to 2/3 our alpha beta components times alpha beta components of the voltage times our alpha beta components of the current. So if you're not clear of how to get here, I recommend watching the other videos. Now this we can write as 2/3 of alpha beta. Yes, so we're just multiply each component and then add them up. Okay, now we know that our phasor in alpha beta is equals to our component in alpha plus j our component in beta. And similarly, our current phasor is equals to our component in alpha plus j our component in beta. So if we wanted to write 2/3 our phasor in voltage times our phasor in current, we will actually get that this is alpha, our component in alpha of a phasor times our component in alpha of our current plus J, our component in beta, times J, our component in beta of the current. And if we look at these two equations, they are not the same because we have the property that J times J is equals to -1. So we need this one here to be negative. So for this one to be negative, we have to conjugate this phasor. So that is our equation. Our total power fed to our machine is gonna be equals to 2/3 our phasor in the stator times our conjugate current phasor in the stator plus our voltage phasor in the rotor times our conjugate rotor current phasor. But as I said before, we cannot add these two, so we need to change these ones into the stator reference frame. Now, how we do that? We know that we have talked about this before, and this is what we do is adding or subtracting an angle. So if we want to get the rotor voltage in the stator reference frame, we get and subtract an angle. Okay, if we have the rotor voltage in the stator reference frame minus an angle, we get the rotor voltage in its rotor reference frame. And similarly, we can get the rotor current in the rotor reference frame by taking the rotor current in the stator reference frame and subtracting an angle. So if we have the rotor current in the rotor voltage in the rotor reference frame and we add an angle, we are gonna get the rotor voltage in the stator reference frame. So that's how we jump from one reference frame to another. So let's do this. We have our equations for our rotor, and we are gonna change it. We're gonna change the reference frame. So we are gonna get R2 rotor current in stator reference frame times minus J epsilon plus R2 derivative of rotor current in stator reference frame times e to the minus j plus L naught dt. Now here in the equation we already have the stator current in the stator reference frame, so we do not have to change it here. Okay. So we keep going. We have R2, our reference frames, the angle, R2. Okay. And now we need to do these derivatives. So this is equals to Okay, I'm gonna write the first one here. Well, actually, this is when we derive a multiplication of functions, we can do it as derivative of the first. This will be our first. So we have R2 dt, our rotor current in our stator reference frame, times the second. So our second will be e to the minus j e epsilon. Okay, this is plus L2. Now we do the derivative of the seconds times the first. So the first is gonna be a rotor current in a stator reference frame times the derivative of the second, that is e to the minus ja. Now we have L naught, and again we do the same. We are gonna get L naught e to the minus j dt, our stator current in our stator reference frame, plus L naught stator current in our stator reference frame d e to the minus j. Excellent. Okay, so let's think a little bit about what this means. Okay, so that we have two reference frames. We have, let's call this our stator reference frame. So we have our here alpha s, and we have here our beta s. And with another color, I'm gonna write our rotor reference frame. So here we are gonna have our alpha r, and here we're gonna have our beta r. So the separation between these two reference frames, the angle between them is epsilon. So, and now we have to remember that these reference frame are for a vector that is rotating. So when the r is rotating, this angle is gonna change. So if we have dE dt is gonna be equals to omega r t in electrical. So we can say that the derivative of e to the minus je is equals to the derivative of e to the minus omega rt. Well, this is j. So this is gonna be equals to minus omega r j omega r in electrical, minus je. Okay, because epsilon keeps being this. Okay, so if we apply that, we just need to, whenever we have this derivative, we have to put this. So we're gonna have here that our voltage equation is gonna be this. So whenever we had our derivative, for example here, mu R2, our current in the rotor with the stator reference frame. So we have here L2, current in the rotor with the stator reference frame, and minus j omega e to the, now remember this is in electrical. Okay, Now we can see that in every term we have e to the minus ja epsilon, so we can just get rid of it. So if we delete it in every part, we are gonna get this. And this is our rotor voltage equation in the stator reference frame. Now that we have this, we can actually calculate the power. So I'm just gonna, because we need the two voltages to calculate the power, so I'm just gonna write it here. Our stator voltage equation in our stator reference frame. Okay, now we are gonna say that our power in is gonna be 2/3 the real part of our voltage in the stator reference frame times our current in a stator in the stator reference frame plus our voltage in the rotor in the stator reference frame well, this is conjugated times our current in the stator current in the rotor in the stator reference frame, and this is conjugated. So our power in is gonna be 2/3 the real part of what we found here, this, times our current in the stator reference frame, plus what we found here, times our our rotor current in our stator reference frame conjugate. So this is our equation for our power in. Now, for our electromechanical power, we are gonna say that we're gonna have 2/3 of the real part of whenever we have the electromechanical part. So it will be this. Well, this is minus j omega r electrical L2 times our current in the rotor in the stator reference frame, and we will multiply this by its conjugate. So this will be one part plus the other part where we got the electromechanical is this, and again this is actually minus omega r electrical L naught I s times ISR. Now, if we look at this, we have a property that says that a phasor times its conjugate will be the magnitude square. So if we have here the magnitude square, we will not have any real part. So no real part here. So we are gonna have 2/3 of minus j omega re L naught is times isr. This is conjugated. Okay. So now we can take out all of the constants. So we are gonna have 2/3 omega re L naught that multiplies j is times isr conjugated. Okay. Now, and we want the real part. Now, if you think about it, when you multiply j times this, the real part and the imaginary part are gonna get switched. So since they are gonna get switched, we are gonna have the 2/3 omega re L naught, and we actually gonna have the imaginary part of this without this minus. Conjugate. Okay, so if you want, you can expand these phasors in is Cartesian form and try to do it, and you will see the imaginary and the real part will switch. So that's why the real part of this is equals to the imaginary part of this. And this is our equation for electromechanical. Now we have also said that power is equals to torque times the speed. So if we want torque, we can, or develop torque, we can say that it's going to be 2/3 omega re L naught, the imaginary part of the multiplication of isr conjugated divided by the mechanical speed. We know in the previous video we saw that the relationship between the the electrical speed and the mechanical speed was the number of poles over 2 times the speed in mechanical. So we are gonna have this is gonna be 2/3 p over 2 L naught, and we want the imaginary part of the multiplication of is times sr conjugated. Okay, so this is another of our equations. So now let's think about how the power goes and how our losses are in the motor. So first we're gonna have our initial power, the power in, and this is gonna be in the stator plus the rotor. So the first thing that we're gonna have losses is copper losses. So the losses that we know that are done just for the copper that the windings are made of. Then we are gonna have losses due to the core, the current and all that good stuff. So if we have the power in and we subtract the copper losses and the core loss, we are gonna get our electromechanical power. And now we can have our mechanical losses. and this is friction or the wind, so windage. So if we have our electromechanical power and subtract this, we are gonna get the power in the shaft. So this is our relation of power. So we just figure out this equation for our developed torque, and remember at the beginning we said that our developed torque was also all of our torques together. So these two are equals. Okay. I don't know why it's acting up. Okay. Okay. Now these two equations are equals. So we can say that this is our mechanical equation. So this is how we calculate torque in our electrical machine and our power.